Welcome back. In our last video, we considered the Cauchy's theorem, the Cauchy's first integral theorem, as well as the proof of the Cauchy's first integral theorem. Remember, the theorem tells us that the function is single-valued and analytic throughout a simple connected region, and if that holds, then the line integral on f of z with or around any closed curve within the region would indeed be zero. We also proved that extensively. In this video, we will look at an example that verifies this Cauchy integral theorem by evaluating the integral f of z dz, where f of z is equal to z squared, around the square by joining the points z equals 1, z equals 2, z equals 1 plus I, and z equals 2 plus I. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos. Now, in order to have a bit of clarity as regards to what exactly is going on with this kind of function, let us have a rough sketch of the regions bounded by this function. So it's not going to be anything over the top, just some simple diagrammatic representations of this function. Now we are going to plot the points of this function as it is. So we'll start, of course, we'll start off on this side. So we can have this as 1, 2, and 3. And then on this side as well, we can have this as 1, 2, and 3. Right? Now the first point is z equals 1, which means the real axis is 1, the imaginary axis is 0. So that exists here. Then the next point is equal to that exists here. And then you have z equals 1 plus I, that is real axis 1, imaginary axis 1, that exists here. And then you have 2 plus I, so real axis 2, imaginary axis 1. So, of course, this is a rough sketch, right? We are trying to represent a scale of 1 centimeter to 1 unit. So, if we connect this, this would be a good similitude of the region bounded, the simply connected region here that this function operates in. Now, of course, we can name the edges A, B, C, D, and if we are to evaluate the integral, we would have to evaluate the integral along all the paths within this region, which is along AB, along BC, along CD, and then along DA. Once we now evaluate that, we add the results together, we will then see if it verifies or satisfies the Cauchy's theorem, which means the integral of f of z should be 0 at the end. Now, let us see if that is true. The very first thing we need to do is, of course, make a representation of our function. Remember, the very first thing is we want to rewrite the function based off the variables x and y. So since x plus iy represents the basic algebraic form of the complex number, it therefore means, as always, that the z would be dx plus I dy, as always. Now, of course, in this case, we know that f of z is equal to z squared, which, of course, would mean that this is x plus iy all squared. So if we expand this, we realize that this would expand into x squared minus y squared for the real part plus I to xy for the imaginary part. Now put this all together into the function. The integral over c of f of z dz would simply be the integral over c of the function x squared minus y squared plus I to xy multiplied by the differentials, which is dx plus I dy. And then, of course, we can expand this so that we can have the real part of the integral and, of course, the imaginary part of the integral. So, if we expand this, we would have integral over c x squared minus y squared dx, right, plus I x squared minus y squared dy, right? So that satisfies the first part. And then we have cos plus I 2xy dx, then minus, because I times I is I squared, you have 2xy dy. This is what we have. Now, if we collect like terms, this would mean that we would have the integral over c for the real part of the integral, x squared minus y squared dx minus 2xy dy, and then plus I integral over c. For the imaginary part of the integral, we would have, of course, this and this, which would be x squared minus y squared dy plus 2xy dx. So we now have these two integrals, our p and q, if you want, and then we evaluate the integrals along the path. So now we'll start from A to B, from B to C, from C to D, and then from D back to A, right? So this would be our representation. Now let's begin. Along AB, right, along the line AB, what do we have? We have that for the line AB, which is of course this, we can take the axis to be from 1, 0 to 0. That's what we have along AB. Now, if this is the case, we see that the equation of the line is y equal to 0, which means that the y equals 0 immediately. Now, if that's the case, then we'll see that this integral that we have here will be affected by these coordinates, as always. Now, if that's the case, what will be left? We'll see that the integral along AB of f of z dz, which is the first one, this time around will now be, since the y is 0, this and this would vanish immediately. Anywhere we see y turns to 0, which immediately vanishes this as well. So what is going to be left is x squared, because this is 0 squared. This is vanishing because of the y, and y, of course. This is vanishing because of the y, and this is vanishing because of y being 0 values. So if that's the case, what is going to be left is going to be the integral. Now, since the equation of the line is y equal to 0, which means the x value is what is consistently changing, it's changing from 1 to 2, so that the lower bound is 1, the upper bound is 2. And then the function remains x squared dx. So you notice that is what is left. That is what is left. So if we integrate this simply, what we are going to have is we're going to have x cubed over 3 from 1 to 2. So this, of course, gives us 8 over 3 minus 1 over 3. So it means immediately that the integral of f of z dz along AB would simply be 7 over 3. This is our first integral along AB. When we move on along BC, right, what happens along BC? We see the line moves from 2, 0 to 2, 1. That's what we're going to have along BC, from 2, 0 to 2, 1. That's what we're going to have. Now, if it's moving from 2, 0 to 2, 1, what we can easily see is that x is now the fixed one. So we have x equal to 2 being the equation of the line, and dx would be equal to 0. By this representation, we'll see that this and this will vanish because dx is 0, and then the others will remain because x is 2. So the integral along BC of f of z dz would now be, of course, y is the changing value from 0 to 1. So we're going to have this going to be integral from 0 to 1 on the first side. This would now have reduced to 2 squared minus y squared, right? This is times 0, so it cancels out, right? And then this is what remains. So we have minus 2 multiplied by 2y dy, right? And we can shorten this. So we have plus I integral from 0 to 1. This vanishes. So this remains. We have 2 squared minus y squared dy, right? So if we write it in short, we would have this to be integral from 0 to 1 minus 4y dy plus I integral from 0 to 1 4 minus y squared dy. This is what we have. So if we integrate this, of course, on this end, we're going to have minus 2y squared. And then here we're going to have plus I into 4y minus y cubed over 3, all of which is going to be evaluated from 0 to 1. This is our representation in this case. Now, if we have this, how do we solve? Of course, upper bounds first, we're going to have minus 2 plus I into 4 minus 1 over 3. And then the lower bound, which is 0, cancels every other thing out. So we have just the upper bound remaining. So from here, we see that the integral along BC of f of z dz would simply be minus 2 plus 11 over 3i. This would be the integral of f of z along BC. Now, this is very, very interesting to note. So we have a value of the integral along AB. We have a value of the integral along BC. We will also have a value of the integral along CD and DA. And putting them all together, adding them all together, will give us the integral over C. So let's move on to the other two parts that we have. Along CD. Now this time around for CD, we see that we move from 2, 1 to 1, 1, right? Now, if this is the case, what do we see? We see that, again, the y is fixed. So the equation of the line becomes y equals 1. And of course, that implies that dy is equal to 0. dy is equal to 0. So what would the integral along CD of f of z dz look like? Well, we realize that since the y is 0, this and this will vanish, and we'll be left with these two. So we can just simply evaluate along those two. Now, remember, the x value is changing from 2 to 1. So the lower bound is 2 and the upper bound is 1. So what would we have left is x squared minus 1 vx, and then on the other side, plus I integral 2 to 1, and then you'd have 2y dx. Or 2xy dx. That's what we're supposed to have. But y is equal to 1. So this is going to be integral from 2 to 1, x squared minus 1 dx plus I integral from 2 to 1, 2x dx. So that's what's going to be left. Now, if this is the case, we would integrate as necessary. We would have x cubed over 3 minus x plus I multiplied by x squared, all of which is going to be evaluated from 2 to 1. Now, if this is the case, we put in the bounds. Both bounds would exist. The upper bound would be 1 over 3 minus 1 plus I, and then the lower bound would be 8 over 3 minus 2 plus 4i. Now, if we have this, we put it all together. The I part is easily mended. The real part gives us a bit of an issue. 1 over 3 minus 1 gives us minus 2 over 3. 8 over 3 minus 2, on the other hand, would give us 2 over 3. Right? So minus times 2 over 3 gives us minus 2 over 3, and you already have minus 2 over 3 here. So both of them adding up together gives us minus 4 over 3, and then this is just I minus 4i, so that's going to be minus 3i. So it means that the integral along CD of f of z dz is indeed equal to this value, minus 4 over 3 minus 3i. And then finally, we complete the motion along dA. Complete the motion along dA, which is from 1, 1 back to 1, 0. So along dA, what do we have? We would see that we're going from 1, 1 to 1, 0. As a result of this, we realize that the x value is fixed at 1, which would mean that the x would be equal to 0. Now, if this is the case, what would that mean? It means that the integral along dA of f of z dz, this time around, we'll eliminate everywhere we have dx, and then only the dy part of the function will hold. And then y goes from 1 to 0. So we have the integral from 1 as lower bound to 0 as the upper bound, and the function remains minus 2y dy plus I integral from 1 to 0. Remember, the dx part goes away, so we are going to be left with 1 minus y squared dy. This is what we have. Now, if we integrate this simply, we are going to have minus y squared plus I into y minus y cubed over 3, all of which is evaluated along from 1 to 0. So from here, the upper bound vanishes because y exists everywhere and y is 0 at the upper bound. And then the lower bound will be left with minus 1 plus I into 1 minus 1 over 3. This is what we're going to have on the lower bound. So this implies immediately that the integral along dA f of z dz would simply be equal to, this is minus 1, that's already plus 1. And then on this side, 1 minus 1 over 3 is 2 over 3. So that's going to be minus 2 over 3i. So now we have gotten the integral along all 4 possible paths around the square. So the full integral, the integral over c f of z dz, would now be the addition of the integral along AB f of z dz plus the integral along BC f of z dz plus the integral along CD f of z dz, and then finally the addition of the integral along dA f of z dz. This would be our addition. And then we have that the integral along AB gave us 7 over 3 plus the integral along BC gave us minus 2 plus 11 over 3i. The integral along CD gave us minus 4 over 3 minus 3i, and then the integral along dA gave us 1 minus 2 over 3i. So this is what we have. Now, adding all of this together, let's start with the real part. 7 over 3 minus 2 will give us 1 over 3. 1 over 3 minus 4 over 3, of course, in this case, gives us minus 1. Minus 1 plus 1 gives us 0. So the real part gives us 0. Now, what about the imaginary part? 11 over 3 minus 3, well, that gives us 2 over 3. 2 over 3 minus 2 over 3, that gives us 0 as well. Thus, it means that the integral of f of z dz is indeed 0. And this indeed verifies that the Cauchy's theorem holds true for this function that is evaluated around the square. So there we go. You'll see that in solving this question, the priority has always been and remains basic step-by-step evaluation around the pathways as presented by the question, right? We did same for Green's theorem. We have done same for Cauchy's theorem as it is. This is very, very essential to note because re-evaluating the function without considering the paths would make you seamlessly change the narrative of your solutions without you even knowing that. Now that we have this, if you have any questions, as always, please let me know in the comments. And if you have any observations to raise, let me know in the comments as well. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos.